Section 16.3 on double integrals in polar coordinates. Well, so this is not going to be the first time you ever get to see polar coordinates. Most likely you got to see this back in calculus too. Typically it's the last section or the last chapter you cover in any calculus 2 class, all right? But still, I'm going to not necessarily pretend you haven't seen anything, but I'm still going to derive these formulas. I mean, those are the formula that you use in polar coordinates. That is to go between polar and rectangle. From polar to rectangle, you go and use these formulas. And to go from rectangular to polar, you get essentially the radius and the angle. Because, well, how does the polar system work? Well, so number one, if we have a point, all right, a rectangular point. What do I mean by a rectangular point? Any point x, y, all right? So another way to describe this point, rather than going length and then width, in either direction, positive or negative, so now we're going to have a different perspective. So rather than going x and y, we're going to move some distance that we're going to call the radius and an angle. So you can think of a camera, for instance. So you are going to point the camera to a point, to a point, and then from there pan the camera at an angle, say 45 degrees, 60 degrees, whatever it is. So let me describe this with this ray right here. So this ray that goes from the origin to the point in question here, so it's going to have some radius, some distance, and it's going to be panned by an angle that I'm going to call theta. All right? Here's the thing. In the end, we should express this point xy instead as r theta. All right? We'll no longer go length and the width or x and y or horizontal, vertical. No, we're going to go distance away from O. The origin is no longer called the origin. It's called the pole. All right? And the reference axis, which is the positive axis, is also called the polar axis, right? So that's the polar axis, which is the reference to go from there to either positive angles, positive orientation, which is counterclockwise, or negative angles and negative orientation, positive, negative angles. Positive, negative orientation, negative angles, that's clockwise, all right? So, that's what you know from trigonometry. So here's the thing. How are we going to get these formulas right here? Well, basic trigonometry, you know? So, this point right here creates a right triangle, for which we can simply use our basic SOHCAHTOA, right? So, sine theta, for instance, which is opposite over hypotenuse, that is y over r, and cosine theta, which is adjacent over hypotenuse, that is y equals r sine theta, and x equals r cosine theta. And that's pretty much all you need to remember from calculus. So where do we get these r sine theta, r cosine theta, which are really a result of doing SOHCAHTOA on a right triangle created or projected by how we go from the pole to the point in question, right? And this distance r, how do we get this distance r? Pythagorean theorem, isn't it? Because you know x, you know y, so this formula right here is just a result of Pythagorean theorem. Tangent theta, that's just the ratio y to x, right? That's from basic trigonometry. So there's not much to derive or keep working on, you know? Okay, so what are we going to do? Let's, number one, graph polar equations, which are typically going to look simpler, or are going to look different in terms of the variables we use. We're no longer going to see x's and y's. We're going to look at r's and thetas, for at least for polar, and then for cylindrical r, thetas, and then z. Well, you'll see about that later. Okay, graph the polar function r equals to 5, and then convert to rectangular form. So when you read r equals to 5, what makes you think of? Hypotenuse, well, the hypotenuse equals 5. What else?
R is the length of 5.
R is a length of 5. But what does R represent anyway?
The radius of a circle.
So there's only one geometric shape that has an R, a radius that is the circle. And yes, you may argue about the ellipse also has a radii, but in this case, there's a major radii and a minor radii for ellipses, right? Not for a unique radius. It's only a circle. So this is really a circle of radius 5, right? Just draw the circle, -5, 5, -5. And 5. All right? Now convert this equation to rectangular form. So you know that R equals to 5. So I'm going to use this relation here. And I'm going to substitute 5 equals to the square root of x squared plus y squared. And then I'm going to square both sides to get x squared plus y squared equals to 25. Does that look like the equation of the circle with radius 5? Center at the origin. So if this circle were I don't know, shifted to the right, to the left, we would see a cosine or a sine term. But well, that's something you most likely didn't calculate. So you're not expected to know all these translations and all those cardioids, limosomes, and butterflies, hearts in polar. I mean, you already had fun with some of those. Now let's do the reverse. So we're given an equation in rectangular. Our job here is to write it in polar because that's what we're going to be doing. Because just to give you a heads up about it, we will run into integration problems that are going to be pretty much impossible to do. However, polar coordinates are going to be our hero here. You'll see. So number one, let's express this function z equals the square root of 16 minus x squared minus y squared in polar form. So every time we want to change from one system to another, your best friend is to see the pattern x squared plus y squared because that's equal to r squared. Well, immediately I don't see it. I need to first 16. Let me factor out the negative. And that equals, in this case, this guy right here equals to r squared. So our new function, z equals to the square root of 16 minus r squared. All right? So notice that that expression no longer has x's and y's. It has r's in this case. Well, potentially it could have thetas as well, but that's not the case. That's something we're going to get to see later. All right. So graphing regions and representing them in in one system and the other. Okay, so let's sketch the region that it's usually called a polar rectangle. What's that? Okay, and it's described by these inequalities right here. Well, the most proper way though to express this is by having this r theta such that so r varies between 4 and 9, and theta varies between pi and 2 pi. So that's the most appropriate way to express it, right? Using the correct set notation, the domain notation, right? But well, we're asked to represent this graphically. So okay, right here, again, r between 4 and 9, that's telling me there's two circles. A circle of radius 4 and a circle of radius 9. Remember when we find domains with functions of multiple variables? But in this case, I gave you functions of x and y. So this is a more simplified and a more compact way to go about. So here is the thing. Okay, let me plot this. So there's a circle of radius 4 and radius 9. So that's radius 4 and that's radius 9. All right? It looks a lot like a donut here. All right? However, I don't think this is the correct region because we have another condition. We have the angle theta that is varying between pi and 2 pi. So if the second condition there about the angle say 0 to 2 pi, well, that's the entire region. However, in this case, since it's only going between pi and 2 pi, it's just going to be the lower part of the donut. So let me rid of this. And let me do this. All right? So that's just going to be half of the donut here. And let's shade the region right here. Whoops. All right. Shade, shade. Okay. So that's how we go about describing the region. So for the most part, we're going to use the polar system well, that's the next part, the change of variables, the integration. When we integrate over regions that look circular, because when it comes to circular regions, typically we would get these radicals with x squared plus y squared that otherwise they may not give us like an immediate way to integrate them, or potentially, as I mentioned before, if they would be impossible to integrate with the techniques that we have so far. So, well, what are we going to do? We're going to make another change of variables, So, dA, which is either dy dx or dx dy, it's going to be changed from xy, from the world of xy to the world of r theta as r dr d theta. I'm going to show you where is this coming from. Well, so number one, let's have a look at this very generic integral, the generalized form. So again, we are going to be given an integral in rectangular form, that is with a function that depends on x and y to choose the best order of integration is possible. If not, well, so we're going to have this new transformation. So we're going to write the function that is given in terms of x and y as a function of r and theta in a similar way we did as in example number 2. So number 2, it's a preparation for this in a way. And then, well, this dA will become r dr d theta, which geometrically I'm going to show you where it's coming from. Later at the end of the chapter, when we get to the generalized change of variables, the Jacobian, we will learn how this r is the Jacobian. What is that? We will see about it later. Let's discuss the limits of integration for a double integral in polar. So unlike an integral in the world of rectangular, for which the inner limits of integration were either just constant values or variables in terms of the outermost variable of integration. In this case, for a double integral in polar, so the inner limits of integration are the radius. And the radius may be just numbers from 4 to 9, from 7 to 23, I don't know. But also, radii may vary by a function of an angle. So that means the inner limits of integration can be just numbers that represent radii or variables in terms of the angle, which is, see how is the outermost variable? So, and the outermost limits of integration have to be numbers that are going to be angles, right? Theta. All right, let's have a look at one example to see this in action, see how it works, okay? So, let's evaluate the double integral 3x plus 4y squared dA, where R is the region bounded by the circle of radius 1 and the circle of radius 2. All right. It doesn't seem like a very harmful problem, but you'll see. So number 1, let's plot the region of integration here. And again, let's draw the circle of radius 1, that's the unit circle, and the circle of radius 2. So that's a unit circle and circle of radius 2. All right? So and shade the region of integration. Now, here is the thing. I'm going to shade the entire donut here because there's no additional conditions. For instance, like in the previous problem where we described the polar rectangle. When we described the polar rectangle, and what's that? We just shaded the bottom part because we had an additional condition, only quadrants 3 and 4. All right. So let's have a look. Let's write the domain first of all. Let's write the domain of integration. That is, we're given this xy such that, how are we going to state the domain using the set notation for rectangular? Well, here we have both x squared plus y squared greater than 1 and less than or equal, greater than or equal 1 and less than or equal to 4. Let's change this to the world of polar. So we're going to go from xy to the world of polar, that is r theta, such that the radius r varies between about 1 and 2, and the angle theta varies between 0 and 2 pi. All right? Okay. So let's rewrite this double integral. So let me rewrite the original problem first. That is the double integral over the region R of 3x plus 4y squared dA. So in this case, I'm just going to go with dA because in the end, I'm not going to evaluate this integral by iterating x or y and x. No. See, in this case, I'm going to go directly from the world rectangle to the world of polar. Okay, so number 1, that's the double integral. Let's write. Okay, let's recall. Let me write something at the top right here. Okay, let's recall that x equals r cosine theta, and y equals r sine theta. So this is what we're going to do here. So we will replace every instance of x with r cosine theta, and every instance of y with r sine theta. All right? So that is 3 times r cosine theta plus 4 times r sine theta. Don't forget to square it. And be careful when you square this, make sure to square both the r and the sine. All right? So, and dA will become r dr d theta. Right? Notice there's a factor of r that shows besides the dr and d theta. Well, actually, once we're done with the first example, because first I wanted to show you how it works with one example, then I'm going to go back to the definition to show you where is this r dr d theta coming from. Okay, so the limits of integration, we have them. They vary between 1 and 2 and from 0 to 2 pi. So the rest of the problem is to get our toolkit, evaluate using all techniques from Calc 1, Calc 2 to evaluate this, okay? So that'll be the integral from 0 to 2 pi, from 1 to 2. Okay, let's reduce this first. So that'll be 3r cosine plus 4r squared sine squared theta times r dr d theta. Okay, let's keep going. So you don't want to integrate this, keep distributing this r right here. So I'm going to distribute the r that multiplies the dr d theta over the two terms right here. So that'll be the integral from 0 to 2 pi, and then from 1 to 2. That is 3r squared cosine theta plus 4r cubed sine squared theta dr d theta. Okay, let's integrate with respect r. So again, what in the end we're doing partial integration. So all we're going to worry about is integrating r squared. The 3 and the cosine are just multiple constants. Well, the integral of r squared, what's that? Isn't that r cubed over 3? Which divides out with the 3. And then the integral of r cubed, isn't that r to the 4 over 4? Which divides out with that other 4 in the front. So let's do that. That is, okay, the integral from 0 to 2 pi times r cubed cosine theta plus r to the 4th sine squared theta, evaluating between, what's that, 1 and 2. All right? Don't forget the d theta right here. But again, where are we going to evaluate this 1 and this 2? Only wherever you see the letter r. Again, because we integrated with respect to r. Theta, it's still a constant at this point in time, right? Okay, so that's the integral from 0 to 2 pi. So we're going to do 2 cubed minus 1 cubed cosine theta plus 2 to the 4th minus 1 to the 4th sine squared theta, not just sine, all right? D theta. Okay, what is this? 2 cubed minus 1 cubed, which is 1, that's 8 minus 1, is that 7, and then 16 minus 1 is 15. Okay, so 7 and 15. So that's going to leave us with the integral from 0 to 2 pi of 7 cosine theta plus 15 sine squared theta d theta. So that looks a lot more like calc 2 integral, not calc 1, calc 2. Well, the first term is just a calc 1 integral. The second one, maybe not. Okay, let me split this into 2 separate integrals so you can see it. So that is 7 times the integral from 0 to 2 pi of cosine theta d theta plus 15 times the integral of sine squared theta d theta from 0 to 2 pi. Okay? So again, the first integral is just an immediate integral that's equal to 7 sine from 0 to 2 pi. No problem. We'll deal with that one in a second. However, the second integral, that's the one I'm worried about. What about it? Because it's not just sine, it's sine squared. Can I use a u substitution? No, because I don't have the derivative of sine multiplying with d theta. If we had a cosine factor, then u substitution. What can we do then? Using a trig identity, right? So we need one of those power reduction identities. That is, let me write it down. Sine squared theta equals to 1/2 1 minus cosine 2 theta. If we had a cosine squared, that's the same identity, but instead of the minus, it would have been a plus. That's how we get these two identities. Well, let's replace. So, should I? Yeah. Okay. Let me save it for later. Okay. So that equals 7 times the integral from 0 to 2 pi cosine theta d theta. So what I usually do is just I save all the integrals when I have all of them ready to be integrated. But if you want to integrate this already, then that's up to you. So that's plus 15 times the integral from 0 to 2 pi 1/2 1 minus cosine 2 theta d theta. So that splits further into 2 more integrals. That is 7 times the integral from 0 to 2 pi of cosine theta d theta plus 15/2 the integral from 0 to 2 pi of 1 times d theta, that's just d theta, minus 15/2 integral of cosine 2 theta d theta, also from 0 to 2 pi. So we're ready to integrate these 3. So the integral of cosine, that's sine. So that is 7 sine theta. The integral of d theta is just theta times the coefficient 15/2 And the integral of cosine 2 theta, careful, because the integral of cosine 2 theta is sine 2 theta times a half by a mini u substitution. You don't have to do the mini u substitution, but that will require a factor of a half that will get multiplied with the 15 halves. That is minus 15 halves times half cosine 2 theta from 0 to 2 pi. Okay? So what's going to happen here? Check this out. So, let me simplify the multiplication here. 7 sine theta. Right, 7 sine theta plus 15 halves theta minus 15 fourths cosine 2 theta from 0 to 2 pi. Okay? Upper limit minus lower limit. So, okay, here is the thing. Notice 0 and 2 pi are going to output the same values for the sine and cosine function, right? Yes.
Why is that why is that cosine 2?
Which one? This one?
Yeah.
Because of the identity. So we wrote sine squared.
After integrating, why is it cosine 2?
Oh, wait. This is supposed to be sine, right? Sine. The integral of cosine is sine. Integral of cosine is sine. Thank you. Okay. What is sine of 2 pi? Isn't that 0? Sine of 2 times 2 pi. Sine of 4 pi. That's also 0. It's the same as sine of cosine and sine of 2 pi and 0 also, right? So all these terms are just going to get zeroed out. 0. The only term that survives is going to be the 15 halves times 2 pi minus 0, which is 15 pi. Oh, come on. That's 15 pi. All right? And yes, that's the value of this integral. No, it's not an area. In fact, this must be what? This must be volume, right? Because of the type of integral right here. It's a double. It's a function, right? It's other than 1. Okay. So let me go back to the definition of how we change from dA to r d theta. All right. So I wanted to show you an example first and then show you the derivation. Okay. So here, in the end, we want to integrate over a circular region or a sector of a circular region. So think of this pizza slice. All right, let's think of this as a New York style pizza, the tinier one, right? So because then we're going to do the cylindrical, that's going to be a Chicago style pizza. I'll show you the difference later. But for now, since we're working on planar regions and not volume, so let's see. How are we going to go from dA to r dr d theta? How are we going to do that? Well, so it's all about the deltas, right? So in this case, let's take one sector, one piece of this sector. All right. So what about it? So this is the origin, if you will, and these are different radii. All right. Let's call this R1 and R2, all right? Together they will comprise delta R, all right? Because final minus initial or 2 minus 1, that's always a delta, right? An increment. All right, so from here we're going to pan this pizza slice from an angle 1 to an angle 2, right? That's going to be some delta theta, right? Okay. So here is the thing. We want to find the area of that sector in red. How do we get area in general? How do we get area in general? I know it's a little weird for this twisted shape, right? Without integration, just geometrically. I mean, it's length times width, right? But that doesn't look like a length. That doesn't look like width. That's why we call it polar rectangle, because it's like a rectangle. It's twisted circular because of the angle, because of the radii. But it's still length times width. So area, or delta area, it's equal to the delta length times the delta width. All right? Well, what about the length? Let me think of the length as the delta r, all right? Delta r, but the length, the delta width, it's not just delta theta, that's just the difference between the two angles. However, do you guys recognize this length right here from basic trig or basic geometry? What is that? I'll give you a hint. We denote it S. What is that? Not surface area. No. We're talking about length, huh? Arc length. How do we get the arc length? Isn't that the radius times the angle? In this case, the difference between the angles, delta theta, and this is where r, delta theta. Now, this is just the area of one finite element of a circular shape, you know. Again, Riemann sum, apply it to the circular region and adding infinitely many of those in that region. What is that going to give us? Doesn't that take us from deltas to these? And that is where this r d theta is coming from. All right. Let's see.